In this video, we're going to learn about the mole. So here's a question. How much water is in my glass? This is a question that you can answer in different ways. So for example, you could measure the mass of the water, you could measure the volume of the water, and those would be pretty easy to do. But as far as the number of molecules of water that are in the glass, that's something that's, well, difficult. Atoms are way too small to count, molecules are way too small to count. I do know that the formula of water is H2O, which means that for every one oxygen atom, there are two hydrogen atoms. But whether we have 20 hydrogen and 10 oxygen, or 2 billion hydrogen and 1 billion oxygen, um, tough to tell, right? You can't just count. Um, so a solution would be that we could take something that's easy to measure, like mass, and then figure out how that relates to the number of atoms or molecules, and that could answer your question of how many atoms of hydrogen and oxygen and how many molecules of water are in the glass of water. And to do this, we have something called the mole. Now, the mole is 6.02 times 10 to the 23rd. It's just a number. It's kind of like a dozen. We have the name dozen that represents 12. Well, the name mole represents Avogadro's number, 6.02 times 10 to the 23rd, whether it's atoms, molecules, or pencils. Of course, in chemistry, we'll be thinking of atoms or molecules, sometimes electrons. And so that's what we'll use. Now, that number is bizarre, right? 6.02 times 10 to the 23rd. It's huge. This isn't simple like a dozen. But there's good reason for it, because the atomic mass in AMU of an element is equal to its molar mass in grams. So, for example, we know that one atom of carbon 12 weighs exactly 12.000 AMU. And so a mole of carbon 12 atoms, which is a lot of them, it's Avogadro's number of them, they will weigh exactly 12.000. But notice it's grams, not AMU. So an atom will weigh a certain number of AMU. A mole of atoms, or 6.02 times 10 to the 23rd atoms, will weigh the same number but in grams. And just for a comparison, we could say that copper, right? Copper, if you look in the periodic table, its atomic mass is 63.55 AMU. So a sample this big, weighing 63.55 grams, contains 1 mole of copper atoms. Aluminum, 26.98 grams, would be also 1 mole. And mercury, 200.59 grams, would be 1 mole. Note that all of these samples, although their masses are different, they contain 6.02 times 10 to the 23rd atoms. So let's do some problem solving. A chemist needs exactly 2.5 moles of carbon for a reaction. How much mass of carbon should that person weigh? Right. So here's a case where, say, we have a chemical reaction that's always dealt with in terms of sort of numbers of atoms or numbers of molecules. And so, of course, measuring, you can't just count out atoms or molecules. We need to use something that's easy to measure, like mass. So we can go from mass to moles, or rather, in this case, from the 2.5 moles to mass. So what we can start with is our 2.5 moles of carbon. And what we'll do is we'll multiply this by a conversion factor. There will be 12.01 grams of carbon for every 1 mole of carbon. And that 12.01 I took straight from the symbol in the periodic table. The atomic mass is the AMU on the average atom, but it's also the number of grams in 1 mole of that substance. So this would come out to 30 grams of carbon using 2 sig figs as in our 2.5 moles. So 2.5 moles of carbon weighs exactly 30 grams. Next, in this sample, in this 2.5 mole sample of carbon, how many carbon atoms are there? So to do this, we could go in a different direction. Notice our mole is our starting point, and that's actually kind of like a bridge. You could go from moles to grams, as we just did, by multiplying by the number of grams per mole, 12.01 per mole. But if we're at moles and we want to go to atoms, then we need to multiply by Avogadro's number atoms for every 1 mole. So in this case, we say 2.5 moles of carbon times 6.02 times 10 to the 23rd atoms. This doesn't matter what we're talking about, atoms of carbon or aluminum or anything else. It's always the same, 6.02 times 10 to the 23rd atoms per 1 mole. So that's going to be 1.2, 1.5. Times 10 to the 24th atoms. And I just realized it's actually going to be 1.6 as I did the math in my head. 1.6 times 10 to the 24th atoms of carbon are in the sample. Okay, let's go in a different direction. Let's do a 2-step problem. So if we know that a sample of phosphorus weighs 15.5 grams, and our starting point is right here at grams, and we're trying to figure out how many atoms it contains, you can see we've got to go from grams to moles, and then we've got to go from moles to atoms. So to do this, we multiply by 1 mole over 31.0 grams, and that works for phosphorus. So the molar mass of phosphorus is 31.0 grams of phosphorus for every 1 mole of phosphorus. But from here, we need to go 6.02 times 10 to the 23rd atoms of phosphorus, or anything else, would be 1 mole of phosphorus or anything else. So that is going to be, let's see, we have half a mole. So we have 3.01 times 10 to the 23rd atoms are in our 15.5 gram sample, which is half a mole. So I hope this video has been helpful. Please leave any feedback, questions, or comments in the comment section below. Thank you.